It's our pleasure today to have Dr. Long from the Pennsylvania State University. He's in the College of Agricultural Sciences there. He's an assistant professor in the Department of Agricultural and Biological Engineering, and is physically located at the Fruit Research and Extension Center in Biglerville. Long received his Ph.D. in Mechatronic Engineering at Yanshan University in China before joining Penn State in China. And then before joining Penn State, he worked as a Postdoc Research Associate and Research Engineer at Washington State University and the University of California, Davis. So as we'll learn today, his research is in agricultural machinery and automation, including mechanical harvesting technology for tree crops and robotic solutions for other agricultural applications. So we're looking forward to having you here today. Thank you for making the drive.
Thank you so much, Dr. Turner. Thank you. Do we have just using the keyboard, right? Do we have the pointer? No, no, it's okay. I can just start from here. Oh, this is not working. Oh, maybe I can use the mouse.
If you want to do this one, if you click on the laser pointer that shows here, then people remotely will be able to see.
Oh, yeah. Okay. Yeah. Okay. Yeah. First, thank you so much for inviting me to UPenn. This is the first time I came here. It's beautiful campus and nice weather. So I'm so happy to be here today. Thank you for everything organized for this seminar. So today I'm going to talk some of the research and extension work that we have been doing for the last few years related to the sensing and robotics for specialty crops. So I'm kind of thinking like if everybody knows what is specialty crops, like compared to the row crops and economic crops, specialty crops are more like the tree fruits, vegetables, nuts, everything else. Those are specialty crops. So at first I want to show this picture to you, and then I want to ask, what do you think from this picture? Can anybody want to see what do you think from this picture? Like, yes. The canopy is too big. Okay. So that's a good point. But as you see, most people from general consumers for us, like we just see those apples here, right? So it's beautiful apples, maybe very tasty, and maybe it's expensive, I'm not sure. So those are just for like general public. You see the tree size, that's further step. So for the horticulturist, what they care about for producing the fruits. So the production, how they can bring trees to this level, how they start planting trees, and then to make sure the trees growing like this big, and then getting the fruit in early kind of years and have the full crops. So those are what the horticulturist concern, and the tree structures and how they can manage the kind of the narrow tree canopy or big tree canopy. And also some of the talk about the healthy, like the water is sufficient water nutrients for this tree to grow on for this crop, and eventually, yeah, for that one,
yeah, I think Holly can monitor the Q&A, and if there's something important, I think she can bring it up.
Yeah, just maybe just put it very small here. Okay.
Let's try to move that.
Okay. This, I think, is probably stay. Oh, hide. Okay, thank you. So actually further a little bit more. And also like eventually they care more about the food quality and yield, and then to get the production well. And for the pathologist, entomologist, for example, they care more about like the disease and pest presence in the field and how those can affect the potential affect the fruit, the crops, right? So they're kind of how to schedule the pesticide spraying and how to make sure that the disease cannot spread into other fruits. So, but then for the environment scientists, I'm just kind of general saying for the focus for sustainable agriculture, for example, they care more about how to make this agriculture industry more sustainable. So they care about environment contamination because we do using chemicals and using water and everything. So how to make sure this process is sustainable. So like the water usage and greenhouse gas emission, everything like that. For engineer, especially for the ag engineer, what we care, we actually consider everything from the top, and we're trying to help them to work with everybody in the above there to make sure we have kind of provide precision and efficient solutions to all of those things. Because when you do produce crops, you're involving labor, you're involving machinery, you're involving all kinds of equipment. So how to make sure that what we do is to provide the sufficient solutions. And more importantly, I think we're working with the growers. So what are the needs from the growers? So for example, labor shortage, labor issues is one of the big things for them. So for the engineers, can we develop something automatically help them to do the production and help them to save the labor? So that is important thing. So that also I also call extension work. So we have a lot of work with growers, and then that is extension. I want to kind of give a brief introduction about Penn State Integrated Precision Agriculture Program. So we have myself and Dr. Paul Heinemann, and used to we have Dr. Dana Choi, but she left to Florida, and now we have Dr. Sharon Samani. So 3 of us mainly working on this area, and currently we have 8 students working in different projects. We have some already graduate and also contribute a lot of things into the project. And of course, we have a lot of collaborators and growers working together. And for this program that we are working on 2 different things. One is called sensor-based crop management and decision-making. And the second one is robotic solutions for special crop production. So for the sensing part, we are looking into like here, like water irrigation, and also apply the fertilizer, like nutrient management. We do kind of also for the precision spraying technology as well to help growers to reduce chemical usage and also protect their crops. And for the robotic solutions, we work on the vision system using the machine vision, different camera system, different vision algorithms to identify the objects we need to target and those kind of things. And then we have the robots to do the action to kind of do the specific task. And eventually trying to kind of integrate everything into autonomous kind of platform that it can operate without a human, so we can have a fully automation system. I just want to provide some brief introduction about the 2 parts of the study. One, for the sensing-based part, there's some major components there. The first one is sensing and remote sensing part. So for this part, we merely do the information gathering and processing. So using different sensors and different systems to gather information, can see from satellite information, and then you're using UAV, using the proximity sensing in the field, and also some in-field sensing as well. So different sensor can do different things, what kind of information you want to gather, and after that, how you can process those data you got, and then to provide useful guidance for the agriculture operations. And the second thing is for this sensing is more like it's called variable rate applications. So what the purpose of in-field sensing is more like for the sensing is more like we're trying to find the variations in the particular the site or field or crops. So and after that we found the variations there, we're trying to treat them differently. So that is more like variable rate applications. I have 2 examples here. One is, you see, this is a fertilizer application. So if you kind of do the soil mapping in your field and you find some variations there, and then trying to apply the fertilizer more precisely, then maybe some part of the field you need to apply more, some need to apply less. So based on that, you can do the control the application. And on the right side here is a variable rate spraying based on canopy. So for the tree canopy, they can be large, small, or there's some canopy maybe have some gaps or something like that. So if you spray everything with uniform rate, that it can be waste a lot of chemicals. So the things like what we want to do is to sensing the canopy, and then based on the size, the density, everything like that, we do variable rate control of the nozzles. And then you can more targetedly to apply chemical to the trees and to the crops. And then we are trying to build connections in the agriculture systems that is called Internet of Things. And the group here is, you guys have a lot of work on that and a lot of sensors and communication protocols there to trying to get better kind of data communication and those things. So this I just kind of, we have been working on the irrigation part, and then we used NORA-WAN technology. And then, so the idea is like you deploy some sensors in the field, but then you can remotely access the data from the field. And based on that information, either you can automatically to apply water, or you can also remotely control. So everything, the data kind of communicate through the sensor controller and the users. So this is kind of is a communication network there. And decision support tools. So everybody likes easy use tools for something like if you can click on the phone or just look from the phone, that'll be easy to access data, to use and to do everything that you want to do. You don't need to physically go to the field to do work. So decision support tool, including how to use like the knowledge that we have to get some rules for the specific task, and then develop some kind of tools, interface kind of tools to do easy operation. And automation is part of that as well. So I have two examples here. One is irrigation. So if you have sensor systems set up in the field, and they can give you the information about soil moisture. And then what's the next step? It's if you want to just to kind of get information, that's fine. But also there's a lot of valves in the field. So if we can utilize this information to open or close the valve, that can actually do the automatic irrigation. So and also for the spray as well, spraying now, so we need a tractor, we need a driver to drive a tractor in the field. So driving tractors for spraying for the operator is kind of like tough job. So you have a lot of chemical there. And if we can develop something that can automatically drive in the orchards and the spray, whatever the canopy needs, so that will be the automation part. It's very important, so it can reduce the human labor greatly. Okay, those are the sensor part, and for the robotic solution part, I'll just give example here. See, there's a robotic arm with camera, with cutter, and that tree here. So those are the major part of this whole system. You have Phage robotic arm and task-specific effector. You also have a agriculture objects. So here, in terms of here is like a tree canopy, and we can do branch pruning. We can do blossom and fruitlet kind of thinning work, and foliage measurements, and do some other kind of foliage thinning as well. And you data, you see the major part are including vision system. Vision system is always kind of the first step. You need to, like human eyes, we need to see things and we can do stuff. So in conventional ways, using camera, we can do a lot of image processing, but in current, like recent years, machine, like artificial intelligence, like deep learning, machine learning has been developed greatly. And then it has been utilized for object detection in the field. It's actually greatly improved accuracy and robustness of those kind of work. And then it's a manipulator. The manipulator could be using different type of configurations. It really depends on the task. If you're working in the field that has the tree canopy has very complex branches, you want to make sure that you have very flexibility in the end, but not like need this big space, workspace, right? So it's kind of depends on the task. And also most important is the end effector part. So for agriculture, especially for the special crops, all kinds of tasks, they require very specific end effector to do the work. For example, pruning and harvesting are two types of work. So pruning, you need a scissors kind of cutting mechanism, but for the pruning, you need a kind of finger type of CRISPR. So then you see how to design those. So it's very important to understand like the motion and the force and or torque involved in those kind of tasks. And then after that, we do the dynamic test, and then we kind of thinking, okay, this kind of mechanism works. So we have this end effect design, and we can control the end effect design or control the end effector to do the specific task, and eventually can be integrated with the robotic arms. Okay, those are just kind of general components that involved in our study research project. And then here I'm going to talk a few projects I worked on. So one is sensor-based irrigation and automatic irrigation. And then second one is advanced spray technology for orchards. And then third one is robotic crop load management. I will kind of conclude with some of extension activities, just showing some of those to you guys. For the sensor-based irrigation and automatic irrigation, we actually at the beginning we test like ET-based like evapotranspiration. We also test some kind of thermal sensors to do the water stress index, and also for the water for the soil moisture sensors. We found that soil moisture sensor is a more direct way to measure, and also easy to kind of get the information we need. So this is how we kind of install the sensors in the field. So this one is using the needle group sensors. We dig a hole and then we place 3 sensors. You can see from this one at different depths. So because for the fruit trees, it's typical the root zone can go to 1 meter depth. So we're trying to cover the whole zone. So this is how the sensors actually are installed. And this is a potential sensor. We just put into the middle of the like 2 feet depths. And this is connected to a data logger. So everything we actually purchased off the shelf is commercialized, commercial product. And then we trying to also get the monitoring the data from the field, and based on that to provide some guidance for growers to apply water. We have been working with different growers and see what those information are helpful for them to guide them for irrigation. I think most growers say, yes, we look in the data, so we feel confident that today I'm not going to irrigate because it's not dry yet. And this is another set of systems we put together. We use the watermark sensors, and then you see those are the sensors, and they use this is using LoRaWAN control board, and then we put together. So this one, we actually put the control, the valves together. So this is one of the interface that we kind of using all things talk. Is one of the platform kind of IoT platform that we can use for design this kind of interface. And then we test this in tree fruit orchards, and also put in the open field of vegetables and high tunnel and greenhouse. We have some success, like do the automatic irrigation. We can mostly we can kind of set up thresholds. For example, like goes to -80 kilopascal, then we start irrigation. And sometimes we have some collection problems. If we need to figure out the valve sometimes cannot open for one time, and we need to try a couple of times, something like that. So it's still some communication barriers there. Sometimes maybe the distance issue. We have a little bit far from the controls kind of on the office. The field is a little bit far, but we did have some success in trying to do more of those work and seeing how to provide a more reliable kind of communication between the sensors in the field and the gateway or in the office. So the second one is advanced technology for tree, like spraying technology for tree orchards. So in conventionally, air plus sprayers is the one that actually using a lot in the field. So I'm not sure you guys in the city will not say too much about how the sprayer works. When you see the spray, actually they spray a lot of chemical out, and you can see a lot of drift in the field, in the air actually. So it's a lot of chemical waste. And then the things like when you think about like how to trying to spray chemicals just to target on the tree canopy, but not too much into the air or to the ground, those drift can be a big risk for environment contamination as well. For also the cost of the growers can be high. So this intelligent sprayer here is variable rate, like I just mentioned earlier. It actually, when it goes through in the orchards, it have the LiDAR sensor to sense the canopy and tells you like the density of the canopy at each location. And then you can adjust your nozzle spray, certain amount of chemical to the trees.
Spray, are you mostly spraying things that are solutions? Do you ever spray things that are more particulate based? You know, is everything like completely soluble, like ions dissolve in water, or do you have to have any examples where you spray something that's a particulate, something that's a seed or something like that that would be,
not dissolved in the soil, in the water, right? So most is kind of mixed with water. Most of the cases it's kind of like, so one thing we spray is called lime sulfur, is for thinning purpose. That is a little bit thick. So they also put a little bit oil kind of into that to make more kind of contraction with kind of retain on the surface of the flower, for example. Lime sulfur. Yeah, lime sulfur. So that is for chemical thinning. But I think in most cases for pesticide, just mix with water very well for the solution and then just spray with certain kind of concentration. It's very kind of, so those are a lot of chemical company, they have the label marked out there saying that you need to use this much for how much water. So it's already marked. And then, yeah, that's, yeah.
The variable rate sprayer, you said, changes the amount of canopy. Are you sensing the canopy density in real time?
Yeah.
With the camera?
Yes, that is, you see this LiDAR there. It's in the front here. We also have LiDAR here for control the back here, but this LiDAR is sensing the canopy in real time. You see the distance from the LiDAR and the nozzle. There's a certain distance, so you give you some time to process the data. And when driving speed is about 2 to 2.5 miles per hour, it's kind of feasible to control in real time for this type of technology. Yes. And of course, this is more like the purpose of doing this is to save chemical and reduce the chemical drift. Another one is autonomous sprayer I mentioned earlier. So this actually it's a lot of interest actually going into this area. Like there's companies doing big sprayer with this, and also some companies doing smaller sprayers. So different you can use for different purpose, right? So for the vegetables, for the small fruits, maybe smaller ones are better because they are kind of driving along, and then the row spacing is small and the crops are small. So, but for the trees, maybe the big sprayer and can be covered better area. So, but this is definitely something I think will be very, very useful. Growers like distancing, that if they don't need to drive, like person drive in the field and just send robots there to spray the whole field and come back and something like that, it's very, very, very helpful. So this is the principle, like we just mentioned about the intelligent sprayer. You see the sensor here. I think different kind of sensor has been tested, like LiDAR sensor actually is more reliable one, but also people using ultrasonic sensors and also for using the cameras. And then they found that the LiDAR sensor pretty much more reliable to the environment because you have different lighting condition or dust or something else. So LiDAR sensor has been more successful in this kind of application. And then based on the canopy sensed and then send out the information to the controller, and the controller will control the nozzles to open with kind of the variable rate of chemicals. And this is just a short video showing that we did experiment. You can see the nozzles open actually according to the canopy it detects. Yeah, just short kind of videos. I'm not sure. Yeah, here's in last year we did test in different. This is just one from one field. We found like you can see 60–70% of chemicals. So it's I want to ask kind of like the trees in the field, right? For example, if for this type of technology, do you think like trees in high density will save more, or trees like spray out kind of more sparse can save more?
So I have a question about very spray. So
Yeah.
is it just spraying at a lower speed, or is it just spraying more intermittent? So how does the variable rate?
The variable rate, so each nozzle, there's a solenoid valves for each nozzle, right? So so each nozzle can cover certain zoom. So you can see from trees, you divide to 5–6 zooms. And then for this area, for one zoom, for example, you have nothing. You don't have any canopy, so your nozzle will shut off. But if you have some canopy, but not too much, then you'll probably have 30–40% of opening. So it depends on, like, LiDAR sensor will give you the point cloud data. So it depends on the density of the point cloud you measured. And then you can kind of spray based on that. Yeah. So I think for this study, we found like this actually is pretty sufficient kind of for the chemical saving. And that 70% means if it goes to grower, this 70% savings is a lot, because they spend a lot of money on chemical spray every year. And there's another study that we did for the airflow control. You see, even we do like using the variable rate spray for those smaller trees, we still see a lot of chemical push through and then can be drift into the other row or something like that. So we're trying to see if we can reduce the airflow into the sprayer, potentially focus only kind of the chemical spray only kind of target or the canopy, but not too much kind of pass and then drift it. So we did this kind of called Irish damper system. We control that based on the LiDAR we put. I think it's not to see from here, but the LiDAR also sensing the canopy. If the canopy is small, then we actually open smaller, so we don't have that much air passing through the canopy, and make sure that all the chemical can be deposit on the tree canopy, but not drift on the other side. We found like about more than 50% of drift reduction in the other rows. So we are testing this water sensitive paper to see how the drift reduction can be. And for the sprayer technology part, I was also trying to mention a little bit some other study. Like we're trying to see because when we spray right now, we spray the whole canopy anyway, right? But if there any possible, if we can identify the location of the disease infection or the potential infection area, then we probably just spray those area first and see if we can still have a lot of precision and saving chemicals. So one of the students also working on the disease infection area detection. This is a 5-ply detection. You can see 5-ply. This one, you see the foliage is very different. It's kind of getting a little bit dry, and also later stage you're getting brownish and stuff. So there's some difference to the healthy canopy. And then if we can identify the location of this area, then we can make decisions. So for the 5-ply, you cannot spray anymore. You need to remove the whole part, but we didn't do that part yet. But things like if you identify the location of the 5-ply, and then you can send your robot there, probably cut off this branch area. But for certain disease like apple scab, they still can be controlled at some point. If you find those locations, you can still spray those parts. So this is more like for the site-specific management for the disease. So using machine vision system to detect the potential or already infected areas. And also you. Mm-hmm. Oh, you mean for the sprayer, right? Yes. I think that is probably just within less than 1 second. Yeah, because driving speed we typically set up about 2.5 miles per hour driving in the field. Oh, this one. So yeah, this can be. I didn't put the video here, but we also did a video. We take a video, and then the video can be processed in real time to find the area that infected. So it's also, this can be done in a real time. Yeah, it's just sometimes maybe need a little bit like some milliseconds, but still in a relatively real time process. Yeah, this is also using like the machine learning, deep learning models to, we did labeling those infected leaves and then train the model, and eventually we can detect the infected area. And also we tried a little bit on the UAV. UAV is just trying to see if we can go on the top of the tree orchards and see if we can find any unhealthy canopy, either related to the like water stress or nutrient stress or even disease problems. We didn't do too much yet, but things like we can generate the maps and see the canopy coverage area, and see also to do some of NDVM index map and see, pretty much give some locations saying that have some potential of the unhealthy canopy maybe there, so we can have better kind of management for those tree orchards. Okay, and then the next one I want to talk is called robotic crop loader management for apples. And then this is, I think we have more students working on this project, so I will spend a little bit more time here. So for an apple tree, you can see from the dormant season like this and until harvesting, we have a lot of work to do, right? So in order to get the better fruits, and we need to do at each step to do the right things at the right time. And in the winter, in the dormant season, you see this is how tree looks like before pruning. So this is, you see how many like branches and how messy these trees are, right? So in the first step to do the crop load management called pruning. So pruning means you cut part of the tree branch off from the tree, make sure that the tree will grow properly. And then in the later, after you do the pruning, and then next step we can do the bud counting. So that is also very early. Bud counting is more like in the very late dormant season or just break the dormant. So, and then at time we can see if we can using machine vision system to see how many buds still on the tree, on each individual tree, or even the branch level, and then give us some sense how many apples were going to grow in this tree. And later, during the flower season, you have blossom thinning, and also some area like in Washington, they do artificial pollination as well. In Pennsylvania, we don't have this problem because we have a lot of wild bees and other. So but we care more about thinning. In Pennsylvania, we have too many flowers or too many crops in the tree. We need to remove some of them. And then we go to the fruit stages. It's called green fruit thinning. It's when the fruits are like 10 to 30 millimeters size, is pretty small. And then at that time, we have almost a last chance to adjust the crop load. So either chemical spray or using manual to remove the excessive fruits from the tree to make sure we have right number of fruits on the tree. Eventually it can grow like this tree, have a lot of big, nice fruits. So I will just give very kind of steps for each of those. And we did work on all of those things in the past. And then the first one to mention is about the robotic pruning. So see, normally we're using this kind of like pruner to prune the branches off from the tree. And in order to develop a robotic system for that, we're trying to see how we can, what kind of motion we need, what kind of force, what kind of like mechanism we should use for this type of work. And then based on that, you see with this one is kind of very, first we develop this type of end effector. The reason we do this is because we found like tree structures are pretty complex along the trunk. So we're trying to bring some flexibility in the tree. So when you have the end effector reach out to the branches, you have a little bit maneuver capability there. So we're trying to develop like two degree freedom or 3 degree freedom of end effector to reach to the branch. And after that, we after develop the end effector, we trying to simulate the path, how we can reach out to the cutting points. And this just some of the simulation we did. We're trying to use this 2 different robot system. This one is 6 degree robotic arm, and this is like Cartesian system. So we are trying to see for those 2 type of manipulator, how we can generate the path to reach out to the cutting points, but without a collision with other branches. This is kind of simulation work. The real kind of situation in the orchard may become more complex with the different trees with branches. And here's some of the prototype we developed. You see here is the 2D degree freedom of the end effector, and this one is another one that we developed for cutting. And we found like with this type of flexibility in the end, we can actually reach the branches at different angles, because branches can grow at any angle, right? So how to reach out to the branches are important. So and we can cut the branches up to 1 inch. So that's pretty much like we're trying to keep the pruning rules is like we're trying to keep cut off the big branches that actually take care of 70% of pruning. So if you cut those big branches off first. And also we tried to integrate into a robotic arm, did some tests on this one. But right now we didn't integrate this vision system yet. So eventually we're trying to see if we can use vision and have the 3D reconstruction of the branches, and then using this mechanism to cut the branches. And after pruning, so this is how the crop load at the bud stages. You can see the buds is like this, right? So this is called a silver tip. So this like at the end of the dormant season, very early of bud break. So the buds can be very small. And for this project, we're trying to see if we can count the flower buds at this stage, and then also to see how many buds on a particular tree or a particular branch. Because for the trees, for each tree, how we evaluate the number of fruits can be on the trees based on the size of the trunk. So if the trunk has certain size, we calculate how many fruits on the tree. And also for the branches, the same. We kind of measure the size of branch, and then we know how many fruits can be produced on this particular branch. So it's very important to first step is to detect those buds, and then eventually later on we can see, okay, those buds belongs to this branch or this tree, and we can calculate how many of them are on this particular tree. Those are 3 different stages. We worked on the silver tip, green tip, and tight cluster. So tight cluster is kind of a little bit too late if we are doing the pruning, but it's also good information for the growers to know at that stage how many flower buds actually on the tree and the potential how many fruits they're going to get. And we have had 2 different type of image acquisition system. The first one is with 4 cameras, and the idea is to actually cover the whole tree and have 4 pictures merged together to get 1 tree information and count. And then this one is just 1 camera in the center here. We also take the images, but those are just part of the tree. And then after that, we take images. We actually developed algorithm also to count, to detect the flower buds at different stages. See here, some of them has green tips and silver tip. Some of them has tight cluster, but I didn't show here. But the idea is like to see the different buds numbers or different buds on the branch on the tree. So for this project, next is actually in the spring now, we are testing the end effector to remove some of the buds. For example, this branch, right? If you measure the diameter here, you see it can only bear 5 fruits for example. And if they have 10 buds, then that means we have like 5 buds more if we keep one fruit in one cluster. So it will be very good if we can adjust crop at this stage. We can remove some of excess buds from this stage, will be very helpful for the tree to grow big and healthy fruits. So the next step for this project is we are trying to develop some kind of mechanism as well, mechanism to remove the flower buds. I know this is very challenging because flower buds can be very small and we can detect, but then you need to have some kind of mechanism to remove it. It's another challenge, but we're trying that.
Another question from the chat. Can you repeat the question after I say it?
Sure. Yeah.
What are the numbers after green tip and silver tip?
Oh, the number that is the IOU. I think that's so that means you have the confidence you think about this is for example, this one 0.93 means you have confidence 93% for this is a green tip. So it's more like if you higher confidence, then you're saying that if it's 1, then definitely it's a green tip. So normally if we set up like if above 0.5, then we think that it's accurate enough to be recognized as an object which is think that it should be the objects that we want to detect. Okay, for the flower stages, so what do we do for the crop loader at the blooming stages? For the flower stages, so currently it's more like using the chemical spray for the chemical thinning for the flower at the flower stages. That means we prevent some of the flowers to be produced to the fruits. So this typically happening during like when the flower cluster open at 40%. So for example, you have 5 flowers in one cluster, when 2 flowers are open, and then you start maybe those 2 flowers already fertilized and going to be grow as fruits. So then you want to prevent others to spray chemical on that. And conventionally just spray the chemical to the whole canopy. And since we also did some work on the flower detection, we think that maybe it's possible to just spray targets on those flower clusters and see how it works. And then this image just showing that those are the flower clusters we identified from those tree branches. Mm-hmm. So the question is how we identify the category of the fruits, right? That like eventually is go to fresh market or go to processing, right? So that is more like in harvest time. I mean, a lot of growers actually at the beginning, they can identify they're going to grow for fresh market or for processing. So it's already they're already defined. So because for the fresh markets, you want big fruits, something like that, nice fruits. But for the processing, you just want yield, you want more fruits. And so a lot of times they're already determined at the beginning. But a lot of times sometimes also when the fruit quality are not that good in the harvesting, so they have something happen for example, heel damage or other kind of damage on the fruits. And then they decide to, okay, we're supposed to be fresh market, but now we want just for juice. That it can also, it really depends on the quality. I think the size, everything like that, for the processing. In Pennsylvania used to be very big industry for processing apple, like for the juice, but now a lot of growers turn to fresh market because it has much more value. For example, you sell fresh market more than $1 per pound, but the processing is only like 20 cents or something like that. So it's a big difference there. And then for the flower stages, then we just mentioned about like we're using more target spraying and then so we come up with this prototype last year we test. So the camera is over here. We have a camera, and then we take one image at a time. But for this one, we just kind of stay in our tree and then spray, and then we move to the next one. So it's more like this type of prototype. And then you have one image taken for this branch, and then we can process image and seeing how many flower clusters and location of the clusters are. And then this robot's kind of cartesian system will move the nozzles into the specific location to just to spray that flower cluster. Yeah, I have a short video here. You can see how it works. So you see, from this branch, you have certain number of flower clusters. But for us, we're trying to target each individual flower cluster because we want to spray all of them, make sure that each cluster have expectation is about 2 fruits per cluster at this moment. And this one, the middle one, is a boom type of sprayer. Just we didn't control anything. We just spray along the tree row. And the last one is L+ sprayer. It's just for a conventional spray way. And we found for the system that we developed can accurately detect 93.8% of flower clusters. That means if there's 100 flowers there, flower cluster there, we can detect 93.8% of them. So it's kind of accuracy is made our expectation. Because the trees, you see the trees we worked on is pretty narrow. So that's why this accuracy can be this high. But if the tree actually more complex, we still need more work to do to, I want to go back once. If this tree structure a little bit more complex for like tall spindle trees or more conventional trees, it will be much more challenge there to identify the flower clusters. So we worked from those, you see how kind of simplify the structure of these trees. And then but this is just kind of beginning. So we're trying to see if we work prove the concept from those type of tree structure. And we found for the cartesian target sprayer, we received more than 50% of chemicals. So that is actually the major target we're trying to see. We want to save the chemical, but also perform relatively close to the other sprayer in terms of fluid numbers at the end. The time, so now because we only have one nozzle, so the time is, we need to spray 4 times for the tree. So the time is a bit high, but eventually we're trying to integrate this system into a ground robots so it can be just drive along the tree row and spray, and with multiple nozzles, so we can just spray 1 time for the tree, for the whole tree, right? So that will be the next step. We're trying to see if we can improve the efficiency. Meanwhile, we're trying to maintain the performance of thinning. So this is the fruit numbers afterwards, after spray. So we can see the cartesian system actually had 2.4 number of fruits per cluster. We kind of thinking its expectation is about two fruits per cluster this time. And it can very comparable to the L+ sprayer we worked that we actually conventionally used. So I think this is the performance of the robotic system is pretty meet the requirement. Other like this boom type sprayer is a little bit more because it's very high, and then the pressure actually we observe that the pressure on the top is a bit low, so some chemicals may not deposit into the flowers. So so this is the crop load at the pruning stages. And last for the green fruit stages. So when you see this picture, this is very typical. If we don't do any chemical thinning or any thinning for the flower stages, this is a very typical cluster showing in this green fruit stages. Typically, the cluster has 5-6 fruits, but the tree can only have like 1 or 2, maximum 2 maybe, for the 2 fruits per clusters. So if there's too many fruits, that means there's too much competitions among the fruits. You won't get a big fruits, and you maybe get a lot of kind of small fruits at the end. So it's very important to reduce the fruit numbers at this time, because this is actually the last chance you can adjust your number of fruits. If it's too late, then it's not useful, because when the fruits are this big, no matter how many remove, then it won't work for the other fruits. So like I said, for the green fruit thinning, the conventional way is also chemical thinning, and also can do the manual thinning. Manual thinning, like chemical thinning, is more like a weather dependence. So it's very affected by the weather. So the performance can be very different if you spray in the sunny day or in the rainy day or cloudy days. So the results is not very predictable. So, but this is right now is most common ways to do it, because it's efficient. You can spray big acreage at a short time, so that is needed. And manual thinning is, so you remove manually for like 4 fruits from this cluster. You can imagine how many work we need to do for one tree for 1,000 trees, right? So it's just the two methods using right now, so both have some kind of short kind of a drawback there. So we need to think something else. So the green fruit thinning, robotic green fruit thinning is one thing that we kind of thinking maybe works for this type of situation. And you also see here is also for this system, we think about the machine vision, about fruit removal methods and end factor and integration things. So for the green fruit thinning, for the vision system for this part, we trying to address 2 problems. One is detect the fruits and stem, because when we trying to remove the green fruits, we need to know where are those fruits and how to get the fruits. So first step is we trying to find where are those fruits are, and also the stems. The stem is for cutting. If we need to cut the fruits off, so we need to know the stem location type of thing. So this is so we took a lot of images and do the model training for the using deep learning models, and those are some of the images that after the outcome from the training from the model. You see the mask are the fruits, and we also detect some stems as well. So for this, the accuracy for this is you can see the overall for the fruits is about 83.4% of average precision. But you can see but if we look into a little bit further, if the image appears bigger, like the fruits are in the front or close to the camera, actually we can get a little bit higher accuracy. So that means in the future, if we do robotic thinning, if we can take image closer to the specific clusters, we can get a little bit higher accuracy. But for the stem, it's kind of a little bit lower accuracy, because the stem is very small and is sometimes kind of blocked by the leaves, and so it's a little bit challenge for the stem detection and identification. But also, if it's close, then the accuracy can be improved. And then we're trying to find. Okay, yeah, okay. And then we're also trying to see the orientation of the fruits, and then see how to find the orientation of the fruits. That's easier for us to get robust access to the fruits. And this is the results. We get most of them are within 15-degree error for the detection of the orientation. And this is just some of them that we're trying to develop the mechanism for removing the fruits, and we see if the pulling or stem cutting, which way is better. In the pulling, we found pulling can be possibly damage some of the clusters. So we eventually select the stem cutting method. And this is the simple mechanism that we developed and put into the robotic arms. And we tried some tests in the field for different cultivars. And this is kind of the results. So if we didn't consider about the integration yet, we thought about only consider about the mechanism part. We have more than 90% of cutting success for the fruit removal. And then currently, or the next step in this spring season, we're trying to do more 3D mesh, and then to kind of get the 3D information of the fruit cluster and then get the location of the fruits and orientation. So then we can actually get into the fruits, each individual fruit. So here is just we develop a path planning algorithm to reach out to the individual fruits, and then trying to remove 4 of them, but remain 1 in the cluster. But this is still a lot of work to do. So this coming season in June, we will test the integrated system in the field for the 3D information. I think that's, there's some other project we worked on for the robotic mushroom harvesting. And we did some autonomous frost protection system using the UGV for carry the heaters in the field to do the frost protection. And I did a lot of tests on the harvesting as well. I think that's it. So I would just show very quickly for our extension activity. See, we did some irrigation in the orchards, set up sensors. See this, I just talked to professors this morning, see how much work we need to do in terms of install sensors in the field, and also teach the growers how to use the sensors and to access the data. And then this is for the vegetables we did in the greenhouse, set up the, this actually is we used the IoT for the automatic irrigation for this particular grower. And we did also organize a lot of workshops and just demonstrate different things for the growers, and also some extension educators, and then those and some extension talks. Penn State has a lot of programs for extension talks. We actually participate in them to a different location of the states, and then to provide information about research and also other information. I think that's conclude my presentation. Thank you so much.